Agriculture is digitizing, as we all know. But more specifically, we are making advancements on different aspects. Now, first, we have the monitoring aspect. And the monitoring can include remote sensing using satellite data or drones, or in situ measurements from soil or crop sensors and manual sampling. Now, throughout the years, inexpensive and automated sensors combined with Internet of Things allow us to follow up on the status of the field online and in real time. Now, second, we have the modeling aspect. Different types of models exist to simulate crop growth and soil moisture dynamics, going from very simple models with only few parameters to very complex models with high information requirements. Now, these models will lead to an approximation of the status of our fields, but they may not be as accurate as our measurements. Now, finally, we also have our decision-making aspect that can be based on either the monitoring or the modeling approach, but also a combination of the two is possible. And this is where we decide on, for example, irrigation, and we interact with our fields on top of the observation only. Now, our aim is to predict soil moisture and optimize irrigation scheduling with SWIM². SWIM² combines all these three aspects in a digital twin framework we call the sensor-wielded inverse modeling of a soil water irrigation model. Now, a digital twin is like a virtual representation of a physical system or process that is continuously updated and synchronized with real-world data. It integrates sensor data and models to mirror, analyze, and predict system behavior in real time. In the context of agriculture and soil hydrological modeling, a digital twin could be a real-time soil water balance model that is updated based on sensor data and predicting soil moisture to support irrigation management decision making. Our research focuses on vegetable production in agricultural fields in Flanders, where 3 soil moisture sensors were installed at 15 centimeters depth to measure root zone soil moisture. Since these data may be biased, regular soil moisture samples were also included. Now, as these daily data come in, our model is calibrated using all the data that is available up to that point. And once the model is calibrated, soil moisture can be predicted for the next 7 days by integrating weather forecasts. And this is then visualized on an online platform where then the farmer can decide on irrigation application based on the expected soil moisture dynamics, but also the probability of plant water stress. Now, to illustrate this, I'm presenting a real-time application during a field trial of Belgian endive. Now, on the left side, we see the black line that is the measured daily soil moisture content by averaging the 3 sensor observations, while the black dots represent the composite soil moisture samples. The field capacity is shown in orange, while the red line is the critical soil moisture threshold. Now, the blue line represents the most likely soil moisture simulation, and the uncertainty is represented by the blue band. Now, let's say we are the 13th of August. At that point, we have 70 days of data available, and these data are used to calibrate the model. The resulting parameter estimates are shown on the right. So we have 12 parameters that are estimated here. Now, from here on out, our soil moisture can also be predicted for the next days, and the probability of soil moisture crossing the critical threshold is computed. And based on this prediction, irrigation is planned. Now, this can be done at any point in the growing season. I do have to point out that the model is still quite uncertain when 20 or less days of data are available. But overall, an accuracy of 0.03 can be obtained, which is very high and is similar to sensor accuracy. So now we can not only observe, but also predict soil moisture. Now, to summarize this, our framework is designed to be user-friendly and tailored to farmers, and can be consulted via an online platform, ensuring ease of use without requiring any specialized expertise. And by optimizing irrigation, it enables significant water savings and higher water use efficiencies, making the most of available water resources. And despite the reduced water use, farmers can achieve equal or even improved yields with high quality crops, ensuring both productivity and profitability. Additionally, the automation saves time, and a prediction also allows farmers to schedule irrigation application few days ahead, which results in efficient time. And finally, with low investments and minimal recurring costs, this approach provides an affordable yet highly effective way to enhance agricultural sustainability and efficiency. So my name is Marit Hendrickx, and this was a short introduction on SWIM² framework, which could not exist without the other partners, so thanks to them. I hope you find it interesting, and I would be glad to elaborate on it if you want to know more.